So in our previous lesson, we learned about how position and displacement and velocity and acceleration are all sort of related through derivatives. So to quickly summarize that, we learned that velocity we can find by taking the derivative of the position or displacement with respect to time. And we learned that acceleration can be found by taking the derivative of velocity with respect to time. So what we're doing in today's lesson we're going to look at how to use the inverse of the derivative, so the antiderivative, to sort of reverse this process. We want to look at, is it possible for me to get the velocity by taking the antiderivative of acceleration? Is it possible for me to get position or displacement by doing the antiderivative of velocity? The answer is yes, and that's what we're going to be talking about today. Before we begin, let's go ahead and take a deep breath. And let's get started. So in our lesson today, I want to start with the relationship between velocity and acceleration, because it turns out, as we'll see a little bit later, that the relationship between these two is a little bit simpler than the relationship between velocity and position or displacement. So first, I want us to recall that the derivative of velocity with respect to time is acceleration. So we learned in our previous lesson that when you take the derivative of velocity, you should get acceleration, all right? But we know that antiderivatives and derivatives are effectively kind of like inverse operations, right? So our new key point, the thing we're picking up today, is that this should also work in reverse. If I take the antiderivative of acceleration with respect to time, I'm going to get velocity. The one thing we have to remember, and the reason that I really decided to split this into 2 days, is that we're still going to need to deal with that constant of integration. When we integrate something, we're going to get that plus c, and we need to be ready to deal with that. So we're going to go ahead and go through one example together here, and then I'll give you one that you can try on your own. Okay. I'm going to try and keep the calculus fairly simple on these, so we can sort of practice the skill of understanding what it is that we're looking at. So the acceleration of an object is given by a of t equals 3 minus t. So part A of this is asking us to find a function for the velocity of the object. Okay. Well, what we just learned is that if I take the antiderivative of acceleration, I'm going to get velocity. So what we can sort of do is we can imagine, well, if I have a of t equals 3 minus t, what I could do is I could take the integral of both sides. I can take the antiderivative of a of t with respect to t, and that should be equal to the antiderivative of 3 minus t with respect to t. Okay. Now we just learned that the antiderivative of acceleration will be velocity. So that means that the left-hand side of this thing is going to be v of t. This is the velocity. So v of t is, now on the right-hand side, I've got this nice easy integral. This is 3t minus 1/2 t squared. And then I have this plus c. The idea is that there's a whole family of velocity functions that this could be describing. And by the way, real quick, that shouldn't be surprising. If we know what the acceleration is, this is just telling us how fast we are going faster, how much our velocity is changing. I could be going really slow and accelerating, or I could be going really fast and accelerating. That's sort of what this c is representing. Okay, so now part A says find a function for velocity if this, and you're sort of given some information. We're told that v of 2 equals 3. Well, that means that if I plug in 2, so if I do 3 times 2 minus 1/2 2 squared plus c, that should equal 3, right? And so when I do this, I'm going to get 3 equals 6 minus, one of those 2's will cancel out, and it'll just leave me with, a single 2 plus c. 3 equals 4 plus c. That means that c has to be negative 1. And that means kind of at the end of this thing, I can now state completely that my velocity function is 3t minus 1/2 t squared minus 1. This is the answer to part A. We took our acceleration, we integrated, we used some information about the velocity at some time, and that allowed me to find the actual velocity function. Okay. Now, parts B and C are hopefully going to be fairly easy here, because they're things essentially that we talked about yesterday, right? Part B asks, all right, cool, so find the velocity of the object at time 6. So all I need to do is plug in 6. 3 times 6 minus 1/2 times 6 squared minus 1. That's 18 minus 36 times 1/2. Oh, that's actually also 18. Looks like the velocity is negative 1. And then part C says, okay, determine if the object is speeding up or slowing down at time 6. Okay. Well, I need a little bit more room here. How do we determine if something is speeding up or slowing down? Like, what do I need to do? Right? What we need to do is we need to figure out what is the acceleration at time 6. Well, at time 6, it would be 3 minus 6. I'm just using this function. That's negative 3. And so since the velocity is negative and the acceleration is negative, we conclude that this object is speeding up. Right? So this has essentially been an example where we have shown that we can sort of work backward. If we have the acceleration, we can take the antiderivative to get the velocity. Now let's sort of look at another one of those so that you can practice it. So parts A and B of this problem should be pretty straightforward. They're related to the things that we've done today and that we've done in our most recent lesson. Parts C and D are going to connect back to some things that are a little bit further back. So those ones are things that you'll do by sort of accessing some of your previous knowledge of calculus. So I'd recommend that you pause the video, that you try and do as much of this one as you can on your own, and then we'll take a look at it together. So we're given the acceleration of an object, okay? Find a function for the velocity of the object at time t if, so this is really the same thing as we had in the previous problem. I'm going to take the antiderivative of a of t dt, and that's going to be equal to the antiderivative of 5 over t minus 4 dt. So the left-hand side is going to be v of t, yay, velocity function. The velocity function is the antiderivative of 5 over t. This is one of our special ones. This is going to be 5 natural log t minus 4t, and then we still have our plus c. And then the one other piece of information we were given is we were told that v of 1 is 11. So I will get 11 when I plug in 1 for t. Well, the natural log of 1 is 0, right? So we have 11 equals 0 minus 4 plus c, and so we can see here that c has to be 15. So at the end of part A, we've sort of concluded that our velocity function has to be 5 natural log t minus 4t plus 15. Okay. And then part B is really just a straightforward application of that. They're saying, hence, find the velocity of the object when time is 3. Okay, so I just do v of 3. That's going to be 5 natural log 3 minus 12 plus 15. So that's 5 natural log 3 plus 3. And we could actually just stop right there. I mean, that answer is sort of complete on its own, but it might be nice if we sort of had a sense for numerically what that was. So if I plug this into my calculator, 5 natural log 3 plus 3, this ends up being 8.49. So that's what our velocity is at 3. Okay. Now, I mentioned the parts C and D of this are going to be things that access some of your previous knowledge of calculus. And so part C says, what are the maximum and minimum velocity, that should say velocities, what are the maximum velocity and minimum velocity of the object on the interval between 1 and 3? And you remember, where do we find maximum and minima on a closed interval? Remember that when we want to find maximum and minimum on a closed interval, the two places we check are stationary points, and then the ends of the interval. Okay. Well, conveniently, one of the endpoints of my interval is 3, and I just found what the velocity was there. It's 8.49. So for part C, what I need to do next is, well, let's look at the other endpoint. V of 1 would be 5 natural log 1. Oh, wait a minute. Haha. We were actually given that in the problem, right? I don't even have to plug that in, right? V of 1 we were given in the problem is 11. Right? So we've got v of 1 being 11. We've got v of 3 being 8.49. Right? And then let's see. So I guess the other thing we need to do here is we need to look at stationary points. Stationary points of the velocity. That would mean, where is the acceleration 0? Where is a of t 0? Because this is going to be another sort of potential for us. If I had 5 over t minus 4 equals 0, that would give me 5 over t equals 4. Moving some things around, t would be 5/4. And so this is another value that I need to check. I know this one, I know this one. When I do v of 5/4, if I just take 5/4 and plug it into this velocity function using my calculator, so 5 natural log of 5/4 minus 4 times 5/4 plus that 15. I got this to be 11.1, right? So then what are the maximum minimum velocities of the object? The minimum is right here, 8.49, and the maximum is right here, 11.1. Now part D, so what's the maximum speed of the object? Remember that speed is just the magnitude, the absolute value of velocity. Well, I mean, in this case, all of our velocities wound up being positive, and so it's just sort of a really straightforward 11.1 is the maximum speed. If any of these had been negative, we would have thought of their absolute values to think about what their speeds were. So I hope that makes sense in terms of this way of thinking about the relationship between velocity and acceleration. There is one more thing I'm going to do with this before we move on to position of velocity. So let's take a look at that now. So the one more connection that I want to make here is like, now that we know that the antiderivative of acceleration is velocity, you may be curious about what the definite integral of acceleration is. Like what happens if I take an integral of an acceleration function and then put bounds on it? Like if I do the integral from 1 to 3, what would that represent? And it turns out it's actually really straightforward, and we can actually see it really, really cleanly, right? Really clearly. It turns out that when you take the definite integral of the acceleration from one time to another time, what it does is it gives you the change in velocity on that interval. And it makes sense, right? Think about this for a second. If I do the integral of acceleration, it's going to be the velocity with c plugged in minus the velocity with b plugged in. When you do a definite integral, you're just plugging in the top value to the velocity minus the bottom value to the velocity. We're just subtracting the end velocity minus the beginning velocity. So it's just giving me the change in velocity, sort of like the amount that the velocity changed over that period of time. And it turns out that this is a really, really useful thing to know, because we might be asked to find velocities from values from an acceleration function that we can't integrate by hand. Like this example right here, it says an object is accelerating in such a way that the acceleration is this. Find the velocity of the object at time 3, given that the initial velocity is 5. This problem is in a lot of ways just like the one we did before, right? You might want to take this problem and do, I can just do the integral of both sides. The problem is we don't know how to do the integral of sine of t squared. It turns out that integration by substitution doesn't help us. In fact, there's no way to do this integral like as a basic integral. We have to use some like really, really, really advanced methods, and even then they're only approximations. I don't want to get into that right now. But the good news is our calculator can kind of do integrals for us, right? And here's the thing that I want to get at, right? If I took this thing, if I did the integral from 0 to 3. Now, why did I do from 0 to 3? I did from 0 to 3 because the problem asked about the velocity of the object at time 3, and it told me what the initial velocity was. Initial velocity almost always means that time is 0. So the integral from 0 to 3 of the sine of t squared dt, I could do that on the calculator, but theoretically, thinking about what we did up here, what should this theoretically be equal to? It should be equal to something minus something. Shouldn't it be whatever the velocity is at 3, from this 3 up here, the velocity at 3, minus the velocity at 0? That's the velocity that I have down here. This is in a lot of ways a simple idea, but it can be weird to wrap your mind around. So like pause the video for a moment if you need to, right? So you've got this idea, right? Now the thing on the left, this integral you can do on your calculator. If you have like your TI-84 calculator, if you hit math and then 9, it'll bring up the little integral symbol. If you plug in the 0 and the 3 and the function and dt, and make sure your calculator's in radian mode, if you do all of that, it'll tell you that this integral is negative 0.246 ... and there's going to be more stuff there. This would be equal to, what is the velocity at 3? Well, it's actually interesting. The problem is asking me to find the velocity at 3. This thing is the thing I want to find. Minus, what's v of 0? We're told that the initial velocity is 5, right? So all I need to do now is add that 5 over. If I just add this 5 over, those don't actually cancel. This is where the work actually happens. The velocity at 3 will be 4.75. So it's really, really neat that we can use our calculator to do a definite integral to find a specific value. So I hope that made sense. Like I said, if you need to, like, look at that again, think about it a little bit more, and make sure you're getting a chance to process that properly. The next thing that we're going to do is we're going to move on and we're going to talk about position and velocity. And now that we've sort of got a base for how we think about these things in terms of velocity and acceleration, it should actually be a fairly quick transition over to that. So let's go take a look at that now. Okay, so now that we sort of have this understanding of how integration can take us from acceleration to velocity, we can really use like super similar reasoning to take us from a velocity function to information about object's position or displacement. So again, recall what we learned previously, that the derivative of position or displacement gives us velocity. This brings us to our sort of second key point of the day, that the antiderivative of velocity will give us position or displacement. But remember again that we're still going to have to deal with that constant of integration. We are still going to have to work with that. Okay. So let's look at this example I have here. Right, an object moves in a straight line so that its velocity at time t is given by this function. So I have a velocity function. Part A says, given that the object is initially 3 meters in front of an observer, find a function for the position of the object. Okay. So we're really going to do the same thing that we did previously. Right. We know that our velocity function, right? We know that our velocity function is 6t over t squared plus 9. Okay. So in order to get a position function, what I'm going to do is I'm going to integrate both sides of this with respect to t. Okay. And the left-hand side, should be easy for us, right? This is going to be our position or our displacement function. We often call that s of t. Now the thing on the right is an integration by parts problem. Okay, so I'm sorry, not integration by parts. We haven't learned that yet. Integration by substitution, right? So for this substitution, I need to recognize, hey, wait a minute, this bottom, the derivative of that is 2t. That's going to line up really nicely with the top. I need to do u equals t squared plus 9. That means that du dt is 2t. And then, we always solve for the dt. Du over 2t equals dt. So then I come back over here and I'm plugging these things in. 6t over u times du over 2t. Looks like the t is going to drop out. The 2 will cancel with the 6. I'm getting that s of t, my position function, I still haven't actually done this yet. This is 3 times the integral of 1 over u du. Oh, cool. That means that s of t is 3 natural log u plus c. And then at this point, I can plug this u back in. 3 natural log of t squared plus 9 plus c. So I sort of move to the side to figure that out, right? Now, we're told that the object is initially 3 meters in front of an observer. So what this means for us is this means that this 3 meters, this happens initially means when time is 0. So the position will be 3 when time is 0. Right? So that means I can find my c value by just doing 3 minus 3 natural log 9. This is definitely a calculator thing. So 3 minus 3 natural log 9. This tells me that my c value has to be negative 3.59. And so all in all, I'm getting that my position function, my displacement function, is 3 natural log t squared plus 9 minus 3.59. Right? So I hope you're seeing here that I'm using like basically the same setup, like the same steps that I did in moving from acceleration to velocity. I'm just doing it now to get from velocity back to position or to displacement. Okay. The last thing here, part B, is just asking us, all right, hey, can you find the position when time is 4? In other words, so can you plug in 4? All right. So if I do this, it'll just be 3 natural log of 4 squared is 16. 16 plus 9 is 25 minus that 3.59 that we got. So in my calculator, I'm doing 3 natural log 25 minus answer. Actually, I suppose that should have been plus that up there, huh? So 3 natural log 25. So I got that this was 6.06. Okay? And so There it is. That's our position at that time. At this point, we've essentially done 3 of these problems where we take an antiderivative of something and we use some information to find the value of c. So I'm not going to do any more of those. I really want to get into some of the other connections and some of the other things that we can do with some of these things and make sure that we can make sense of them. So let's move on to that. All right, so just like I did with the velocity and acceleration, we can also take a definite integral of the velocity function of an object. Okay, and very, very similarly, the definite integral of the velocity from one time to another time is really just going to give us the change in displacement, right, over a time interval. So if you do an integral of velocity from b to c, all you're going to do is, we know that the integral of velocity is supposed to be displacement, right? And so this is just the displacement at the end time minus the displacement at the starting time. So all you're really doing is, if you're imagining the thing started here and it ended here, you're just doing the end displacement minus the beginning displacement. You're just finding out what the change in displacement was. Okay? So really, really straightforward. Okay? And so let's go ahead and look at that really quickly here. So the velocity of an object is given by velocity equals t minus 3. Find the displacement of the object from the starting point when t equals 7. Find the displacement of the object from the starting point when the time is 7. Well, what does starting point imply? Doesn't starting point imply that time is 0? So when they say find the displacement of an object from the starting point, they're really saying, all right, what is the integral from 0 to 7 of your velocity function? Right? Wouldn't this like essentially get us what the displacement is at 7 minus the displacement at 0? This would essentially just give us the displacement of the object, how far away it was from its starting point, right? In this case, I'm just going to use this function. Let's do the integral from 0 to 7 of t minus 3. Okay. When I do this, I'm going to get 1/2 t squared minus 3t, and then I plug in 0 and 7. Right? And so when I do this, I'm going to get, let's see here, 49 over 2 minus 21 minus 0 minus 0. Okay, so that's just a whole bunch of 0. Let's see here. So this is basically 24.5 minus 21. So this is 3.5. Okay? So 3.5 is the change in displacement. Now, part B is really important here, and I don't know that I expect you guys to fully get this right now, but the rest of the video is sort of going to be about this next idea. Is this answer in A? Does this tell us how far the object traveled? And why or why not? So I'd encourage you to pause the video and think about that for a second. We just found out that the change from the starting position to the ending position was 3.5. Does that tell us how far the object traveled? And the answer, hopefully you got this, is no, it doesn't. And the reason is, if you sort of imagine that this is where the starting point and this is where the ending point is, and yay, the distance between those two things is 3.5, we're not guaranteed that the thing just went from straight to the end, start to the end. For all we know, the thing went way this way and then wiggled around and did crazy stuff and then wound up here. Who knows? 3.5 is only telling me how far apart the start and end are. They don't tell me anything about how far the thing traveled. And so being able to find that is sort of the next thing, the last thing that we're going to look at and talk about in this lesson today. So to help us wrap our brains more around this, I want to look at what I hope is going to be a fairly simple illustrative example. Okay? So imagine that the velocity of a car, some number of seconds after passing by some flag, is given by this function. So the velocity is 15 minus 3t on the interval from 0 to 7. Okay, so for the first thing I want us to do is I want us to sketch this graph. And hopefully this should be easy because this is like a y equals mx plus b kind of thing, right? I've got on this axis my velocity, and I've got on this axis the time. Okay, the thing's got, an initial velocity of 15, and then the thing is, it's sort of coming down this way with a slope of 3, and so maybe the thing ends over here at 7. In fact, we could even plug that in. When I plug in 7, this should be down here at -6. When I plugged in 0, the thing should have been up here at positive 15. Okay, so this right here, this is sort of my sketch of what the velocity graph, what the velocity function looks like. Now, but I'm going to walk us through this, and every step of this process should be making sense. So if you need to sort of rethink it, like look at it again, because this connects like critically to the thing that we're doing. So I've got a sketch of the graph. So where does this graph intersect the horizontal axis? In other words, what is that point right there? Wouldn't that be the place where the velocity is 0? So it would be where 15 minus 3t equals 0. In other words, this happens when, not when time is 0, happens when time is 5. Okay. What does this represent? What does it mean that the velocity is 0? What does it mean that it happens when t is 5? Right? Doesn't this mean that the car stops at time 5? Like the velocity becomes 0 at time 5. Okay? And now let's actually think more about this. Let's think about this in two different sections. This section here, and then this section here. Okay? So part C is now going to ask me, all right, part C, what is the car doing between times 0 and 5? Okay? What do you notice about this? Because remember, this is a graph of velocity, right? The velocity was 15, and now maybe it's 12, and now maybe it's 9, and now maybe it's 6, and now maybe it's 3, and now maybe it's 0. So what's happening right here is the car has positive velocity. So it's like going forward, but it's slowing down. Sorry for my horrible handwriting right there. During this time interval, the car is going forward. It's got positive velocity. It's going forward, but it's slowing down. What would the area under this curve represent? What would the integral from 0 to 5 of 15 minus 3t dt, what would that represent? Wouldn't that represent the change in displacement from here to here? But if the car's going forward the whole time, that thing would represent the distance that the car went. Because this is all positive, we don't have to worry about, oh no, what if the car turned around and went backward? Spoiler, the car doesn't go backward till we're over here. This is all forward movement, right? So I could just do this integral and figure out what it is. Or sneakier than that, I could actually see that this is just a triangle. It's a triangle that's 1/2 base times height. So it's like, haha, we can sort of like sneak our way through this one. And so if we do that, we find that this is 37.5. So that means the car must have moved 37.5 during that interval. Okay, now switching over to a blue marker here. So what's the car doing between time 5 and time 7? Right? For part D, now the car is like backing up. So during this time, sort of the car's going backward, right? If I were to do the integral from 5 to 7 of 15 minus 3t dt, right, wouldn't I get something negative? Like this integral would wind up being, I mean, it's 6 units tall, it's 2 units wide. This would be 1/2 of 2 times 6, so that would be -6. Does that mean that the car's distance is now -6? Like, no. Right? The fact that this is negative, it just means that the car went backward, right? So when part E asks me what was the total distance traveled by the car, the total distance is going to be the 37.5 that we went forward plus the 6 that we went backward. And you might be wondering, like, wait a minute, like, why can you just make this negative into a positive? I mean, it wasn't like dark magic that I did here. This was just me recognizing, hey, motion that I do going forward and motion that I do going backward are still counted as distance. It's not like if you run a mile forward and then run a mile backward, you're not tired anymore because you didn't go anywhere. Like, we still have to add those things together, right? So the total distance traveled by this car would be 43.5. Okay? So when you're looking at total distance, we need to consider this idea that areas above the axis and area below the axis both contribute to distance traveled. There's one more lens that we can use to look at that, and I'm going to try and look at that really quickly for us so we can end this lesson. All right, so I really want to encapsulate everything that I just said about how to find the total distance traveled essentially into a formula, right? And we can say definitively that if you want to find the total distance traveled by an object with a certain velocity over a time interval, what you do is you compute the definite integral of the absolute value of the velocity function. Because what that does, if you imagine that last problem that we did that was like this, when we did the integral, there was some forward motion and some backward motion. And so if you just did a straight integral, they'd like partially cancel one another out. But if you do the absolute value of velocity, this function becomes this and this, which means all of this negative area gets treated as positive, and so it's able to compute it as the total distance traveled. Okay? Now, I want to sort of note here, actually computing the total distance traveled either requires that we did in the previous illustrative example where we sort of looked at this thing and found this area and then changed this area into a positive, or sometimes you can just use your graphing calculator. If it's a calculator problem, you can just use the graphing calculator to take the definite integral of the absolute value of the function. So this quick example that we should be able to do in less than a minute, use your calculator to find the total distance traveled between 1 and 9 by an object whose velocity is given by this thing. And I promise you, this curve, like it does some like wacky stuff, right? So we would not want to try and do this integral by hand, right? But we can do the integral from 1 to 9 of the absolute value of t sine 2t plus natural log t dt. And on your calculator, like if you're wondering about how to put this into your calculator, what you can do is you can do the math 9, and that brings up your integral. So we do math 9 to get the integral part to come up. And then you put in your bounds, you put in your 1 and your 9. Okay. Then we need these absolute value bars. Okay. To get those absolute value bars, you hit your math menu, which is over on the left underneath alpha. So we do the math menu, you go sideways to num, and then the first thing there is ABS. And so if you pick ABS, it'll put in absolute value bars for you. Then you can just put in, I'm going to use x instead of t, x sine 2x plus natural log x. And then put your dx at the end. And when you hit enter, this thing thinks for a moment because this is a mess of a problem, and it thinks and it thinks and it thinks. And it keeps on thinking. Wow, I really gave this thing a lot to think about, didn't I? Went ahead and paused the video here so you didn't have to wait for me to wait for this thing. This wound up being 26.3. The fact that the calculator had to think for like 30 seconds means that if I was on a desert island and had to do this out of calculator, I would be in a lot of trouble. But because I use these absolute value bars, this gives me the total distance traveled by the object over that time period. So I apologize that the video is long. I hope that all made sense. As always, ask questions if you have them, and I wish you best of luck as you work through the assignment.